Muy buenas tardes a todos, espero que estén muy bien. Bienvenida a este nuevo taller, el curso de taller de conversión de energía. Hoy día vamos a tener la presentación del profesor Patrick Wheeler, de la Universidad de Nottingham de Inglaterra. Él realizó su carrera de ingeniería eléctrica en la Universidad de Bristol, en Inglaterra, y su doctorado también en esta universidad, terminándolo en el año 94. El año 93 se movió a la Universidad de Nottingham y trabajó como un asistente de investigación en el Departamento de Ingeniería Eléctrica y Electrónica, y el año 96 comenzó su carrera académica, integrándose al grupo de electrónica de potencia, máquinas y control en la misma Universidad de Nottingham. El año 2008 pasó a ser profesor titular en este mismo grupo y también fue director del Departamento de Ingeniería Eléctrica y Electrónica entre el año 2015 y el 2018. Actualmente es el director del grupo de investigación de electrónica de potencia, máquinas de control, uno de los grupos más grandes del mundo en esta área, y también forma parte del comité académico de la Sociedad Electrónica de Potencia, y ha publicado más de 500 artículos en diferentes conferencias internacionales y revistas. La charla va a ser en inglés y después de la presentación del profesor, cada uno de ustedes va a poder hacer un par de preguntas al profesor. But thank you very much for participating in this initiative. Now the screen and the microphone is yours.
Okay, thank you very much for the introduction, Marco, and hello to everyone. I'm very sorry that my Spanish is very poor, so I'm afraid I will be giving this presentation in English. Hopefully I can share my presentation. So hopefully you should now be able to see some PowerPoint slides. Has that worked, Mark?
Yes, yeah. It's working.
Excellent. Okay, so I'm from the University of Nottingham in the UK. I've been there for a long time now, about 25 years. And we're very lucky in Nottingham in that we have a very big research group which looks at a lot of topics around electrical engineering. So the research group that I lead is the Power Electronics, Machines and Control Research Group. And we work in areas such as transportation, electrification and energy conversion, particularly for connecting renewable energy to the electricity grid. We're quite a large research group. We currently have about 160 people doing research. So about 60 of those are postdoctoral research fellows, people who have a PhD and continue to do research with us. About 75 are PhD students and about 20 are professors, academic staff. And they're listed on this slide here. So we work in areas such as electrical machines, so the design and the construction of electrical motors and electrical generators. We do a lot of work in power electronic systems, power electronic converters, and that's my area of expertise. We do a lot of work in motor drives, so controlling electrical motors and the stability of the power systems they connect to. And we do a lot of work which we refer to as power electronic integration. So looking at how to manufacture power electronics to make future systems work more efficiently, more reliably, and hopefully more cheap to buy, so lower cost. Underlying all this, we have a lot of work ongoing in thermal management. Whenever you have an electrical system, so the power supply for your laptop or electrical motor, it generates heat, and you need to design how to get that heat from inside that piece of equipment into the air to cool it down. So underlying all of our research is that work on thermal management. We like to build things. So you'll see here some various motors that we've built. The one in the top right-hand corner is an interesting motor because it fits inside the wheel of an aeroplane. So that's a motor designed to move an aircraft around the taxiways at an airport. And that's a demonstrator of a full-size wheel that was tested against the requirements for that particular aircraft. The one next to it is a smaller unit. It's an actuator for controlling a helicopter. So that's an example of a motor and power electronics in a flight critical application, an application where if that unit goes wrong, then you lose the aircraft, the helicopter in this case. One of the things we do have in Nottingham is a very strong ethos of designing, doing lots of simulation, lots of analysis, lots of optimization, but also building and testing the electrical machines and indeed power electronics. So the largest power electronic converter we've built is the one you can see in the bottom right-hand corner there. So that's a 4 megawatt electric motor drive. And that is the sort of power level you need to fly a regional aircraft. So that power converter has been built around the requirements for electric propulsion of an aircraft. There's various other examples there that we've built, some large and some quite small. I'll talk a little bit about some of those applications in this presentation. One of the big topics in electrical engineering at the moment is the electrification of transportation. So making cars, aeroplanes, ships, and so on electric. And so I really wanted to start by why we're looking at this. What's the motivation? And so here we're looking at cars. And if you look on your roads today, you'll find most of the cars are either diesel or gasoline, petrol. And over the next 20 to 30 years, we're going to find that petrol gasoline cars are going to disappear. And they're going to be replaced with cars with electric propulsion. And this chart is interesting in it does not see a single solution. It sees lots of different solutions. So there's a section there for all electric cars, but also sections for gasoline cars that are hybrid with electric motors, for areas of the world where there isn't the supply to be able to charge the cars all the time. So sometimes you might need to use gasoline for some years. And then hydrogen at the top there, probably looking at hydrogen fuel cells rather than hydrogen combustion. But what we can see from this chart is that a lot of cars, a lot of automotive energy is going to be electric propulsion. So therefore we need to have the systems in cars to be able to drive them. So that's cars on roads. This chart is looking at aircraft, so looking at the aeroplane industry. And what's expected to happen here is over the next 30 years, they expect the number of aircraft to double from where it was 10 years ago. I know that we've had COVID and that the number of flights has decreased, but history tells us that that will bounce back and the number of flights will continue to increase again at the same rate as it was doing before COVID. These things cause a blip rather than a permanent change. So what the aircraft industry has been trying to do is to try and reduce the emissions from aircraft. One of the challenges is that an aircraft can last for 25 or 30 years, and to design a completely new aircraft also takes maybe 15 or 20 years. So it takes a long time for this industry to change. So the red line shows what happens to carbon dioxide emissions if there is no action and we keep burning aviation fuel, kerosene, at the same rate. What we want to do is to follow the bottom green line and to bring in new technologies, sustainable fuels, and to make the aircraft lighter and more efficient, and to be able to halve the emissions we had in 2010 by 2050, and also to get back to that emission target at around 2035. That's quite challenging because it takes a long time to change the whole fleet of aircraft. So these technologies have to come in the next 5 to 10 years if we're going to meet that target in 2050. So I want to start by looking at the more and the all-electric aircraft and why there's so much interest in this area. I'll start with the concept of the more electric aircraft. So the idea of the more electric aircraft was that we still had big gas turbines on the wings of the aircraft to provide thrust, to provide the propulsion of the aircraft. And if you look at a long distance aircraft, maybe a Boeing 777, then the thrust from the engine is around the equivalent of 40 megawatts of energy. But also from that engine, we take electrical power, we take compressed air or pneumatic power, we take hydraulic power, and we take mechanical power. And those are used to feed other systems on the aircraft. So the electrical power is used for things like lighting, the avionics, the in-flight entertainment system, and the galleys, so that we have something to do on the airplane and hot food and so on. The pneumatic system is used primarily to pressurize the cabin and provide the air conditioning, the temperature control, as well as ice protection for the wings of the aircraft. And you'll notice there's 1.2 megawatts just used to pressurize the aircraft and to remove ice when you're flying through clouds. The hydraulic system is used for actuation, so to control the aircraft, landing gear, braking, doors, things like that. And the mechanical system, another 100 kilowatts, is used for pumping fuel and oil, particularly around the engine. One of the things we've seen a big trend in, and the Boeing 787 is a good example of this, is going to more electrical systems on the aircraft. So doing the air conditioning and the cabin pressurization using electrical energy, doing the flight controls using electrical energy, and doing the fuel pumping using electrical energy. And the reason you do that is because it makes the design of the engine simpler. We don't need to take the hot air, the pneumatic power off the engine. So that makes the engine more efficient, but also because the electrical energy then is more controllable, and we actually take less off the engine because we can control better how it's used. So you'll see the total electrical power system on a large aircraft is about 1 megawatt, whereas with the 4 systems on a traditional aircraft, we were taking 1.7 megawatts off the engine. So we're taking less energy off the engine and performing all those things electrically. So it's a good time to be an electrical engineer. There's a lot of jobs in trying to make this happen. The other thing we're trying to do with aircraft is to remove the jet engine altogether and replace it with electric fans. So to have an electric motor and a power electronic converter to control the fans on the wings of the aircraft so that we can fly the aircraft with electrical energy on the wing rather than heavy gas turbines. So some big challenges in this, particularly around developing the new electrical power systems. And there's a roadmap of how this might develop. This is one from NASA. We have a similar one in Europe, looking how over the next 10 to 20 years, we're going to get to regional aircraft with maybe 4 or 5 megawatt motors on the wing. And in about 30 to 40 years' time, even the very large aircraft will also have electric motors for the propulsion. This does not mean that they have to be battery powered. It would be nice if they had batteries on them and we could just charge the batteries up, but batteries are a little bit too heavy for that at the moment. So it might be that we have to get the electrical energy from a different source. That might be a fuel cell, or it might be a gas turbine with a generator being run at a single speed to get the optimum efficiency, but also to put that jet engine in line with the passengers in the body of the aircraft so that it does not present a drag force on the aircraft. If it's in line with the people that in the fuselage, then you will get a more efficient flight because you don't have a large, bulky engine sitting on the wing. You'll have smaller, lighter electrical motors. So there's a lot of work going on in trying to make electric motors small enough and light enough and efficient enough to work on an aircraft. And these charts just try to show where we are with that work today. So in the left, you can see a simplified version of the NASA roadmap, and you can see the demonstrators we've built in our labs in Nottingham. And as you would expect from a university laboratory, we are well ahead with the demonstrators of the motors compared to when they need to go on the aircraft. So that's good. The chart in the top right is interesting because this is showing the factors, the requirements we have for lifetime, efficiency, cost, volumetric power density, and weight power density. And you can see that for the lifetime of the electrical machines and the power electronics, we're okay. We're where we need to be. The efficiency is nearly there. The power density, both weight and volume, needs some improvement. And at the moment, everything is too expensive. So we've got to be able to make these things cheaper using advanced manufacturing techniques. So some work there to do to make things smaller, lighter, and more cost effective. And that's the focus of a lot of our research in this area. So how are we going to go forward in both cars and in aeroplanes in making these electrical machines and their drives smaller, lighter, and hopefully more cost effective? There is not one technology that will do this. What we need to do is integrate lots of technological development. So we're seeing things like designing advanced machines using our simulation tools to be able to design machines that we could never make before. We have new materials with lower losses, so we can put those in there. We have new cooling techniques, so we can cool the areas where the heat is actually being generated, and we don't have to have so much material in there to disperse that. We might use two-phase cooling, for example. We can do lots of things with the windings, with the rotor design. We can do a lot of things with advanced manufacturing. The concepts of additive manufacturing or 3D printing mean that we can make machines in shapes and in ways that were never possible even 5 years ago. And power electronic converters is enabling us to feed electrical machines with higher frequencies, as you'll see in some coming slides. And that means that we can make the motors smaller and lighter as well. And finally, there's integration. As engineers, we need to be able to think not just of an electrical motor and maybe the power electronic converter, but of the application that we are dealing with, and to try and put all of that together. And when we do that, we find that we also get a saving in weight and volume. So this chart just tries to show the technologies that are having an impact on electrical machines and their applications. So along Bottom of the chart is technology readiness level. And this is showing us the how ready a technology is to be inserted into a particular application, and then the impact. And you'll see there things like thermal materials and wide bandgap semiconductors and new magnetic materials are the ones which are going to have an impact sooner rather than later. This chart tries to show how we're doing with different machines at different speeds in terms of their power density, and looking over the last decade and the next decade to see where we can build machines that are smaller at particular speeds. And you can see there the power densities all going up. But the other thing you see is that the faster the machine, the smaller the machine is. So going up in speed gives us a big advantage in terms of the power density. So doubling the speed can double the power density of the electrical motor. And that's quite useful. Just being able to go faster makes that smaller. The problem with that is that in many applications, if you make the machine too fast, you then need a gearbox to slow down the speed again, and then you lose that advantage of power density because you've got other parts of the mechanical system that you then have to put in there. So there's always a compromise and a design. In Nottingham, we like to demonstrate things in a big way, looking at how those fit together. And the example here is the motor and the power electronic converter that I showed earlier. It's a 4 megawatt propulsion system designed for a small regional aircraft. It's hard to see in that photograph, but that electrical machine is about the same size as a 30 kilowatt induction motor that might be used in an industrial application. So that motor really is very small for a high power level of 4 megawatts. So we've really been able to get the cooling right. We've been able to use the power electronics to bring the size down. And we've been able to use advanced design techniques to make that machine a lot smaller and a lot more efficient and reliable than we would have been able to a few years ago. So that's probably the most advanced demonstrator we have of an aircraft propulsion motor. Now, when we look at aircraft, it's very easy to think of the idea of just replacing the gas turbine with an electric motor. And that would be simple to do. But electric motors behave differently to gas turbines. And we need to think of the safety of the aircraft and the way we design that, but also to look for ways in which we can make the aeroplane more efficient. And one of the ways we can make the aircraft more efficient, more resilient, therefore safer, is to have multiple fans along the wing. And unlike with gas turbines, we don't pay a big penalty for doing that. So the picture on the left shows a diagram of the propulsion power system of an aircraft, where we've got 2 gas turbines driving 2 propellers, but also driving 2 generators. And the electrical energy from those generators is therefore driving other electric propulsion motors that are situated elsewhere on the wing. So we really do have a distributed propulsion system with lots of electric motors driving fans along the lengths of the wing. The other advantage of that system is we can have some batteries or fuel cells also on that electrical system to drive those electric propulsion motors. So maybe when we're coming into land, or maybe when we're taxiing, you would only use the electric propulsion. You wouldn't need to have the gas turbines as part of that system. So we'd like to call that a sort of mild hybrid. It's a hybrid system for the aircraft. It still has gas turbines, but they're being used far more efficiently because we also have the electric propulsion. On the right-hand side of that chart, we see another option. With this one, we have a gas turbine driving a generator, driving a power converter, and that's driving a number of fans on the wing. So here, the gas turbine and the generator would be in the body of the aircraft, along with the people or the cargo. And the motors are there to drive the aircraft and to provide all the propulsion. So this is a typical series hybrid system. All the propulsion is done electrically. The gas turbine is not connected to the fans at all. All goes through the power electronic converters, which are the green and blue boxes there. And as well as getting efficiency of use of the electrical systems, the other great advantage of this is that the gas turbine is not in the airflow. So we get that efficiency gain. And we can therefore run the gas turbine at its optimum speed all the time. It would either be on, generating electrical energy, or it would be off. We don't need to have it running at inefficient points in that system. This is a demonstrator that we finished last year. So this is a real aircraft engine. It's a turbo prop engine from a regional aircraft. Built by Safran in France. And we took that existing engine and we wrapped an electric motor and a power converter around the gearbox of that engine, which is under the cowling that you can see in the right-hand picture there, to boost the output of that engine. So that allows us to use the same engine on a bigger aircraft. So this was a demonstration of adding electrical power to the drivetrain of that turboprop, putting a slightly bigger propeller on it, but using the same engine as before, but to drive that bigger aircraft. The reason we can get away with doing that is that the peak loading for the aircraft engine is at takeoff, particularly in climb and at the top of climb, where the engine has to work the hardest. Then once you're in the flight and you're cruising, the engine is not working at its maximum power anymore. You drop back a bit. And so the electrical motor here is providing that boost to help the aircraft take off and get to the top of flight. But the other thing that was very good about this is when the aircraft was on the ground, you didn't need to use the combustion engine. You could just turn the propeller using the electrical machine. So a lot of advantages, both in making the aircraft a little bit more efficient, but also in reducing the noise that you get around the airport. So that's an example around aircraft and aeroplanes. The other area that's quite interesting is automotive. We do a lot of work for trucks and cars, but a lot of that is with industry. But the other thing we do is to demonstrate some of this technology on race vehicles. So the example I was going to give as a case study in this lecture is looking at an electric motorbike. So you can see in the picture there, the electric motorbike that we race at the University of Nottingham. And this bike is capable of speeds of up to over 300 kilometers an hour. It's won some races, including the European Track Series for electric bikes and the Isle of Man TT. And it's faster around a Formula One racetrack than a BMW Superbike. The reason we chose the BMW Superbike is that's the bike that our rider races when he races petrol bikes. So he had the same level of familiarity with both the petrol bike and with the normal road bike. So, number of things about this. Why race? Well, one of the reasons we were racing was to promote electric vehicle technology. Motorsport is a great way to raise awareness of new technology, and the TV coverage and media coverage you get is great. Another reason is to push the boundaries of technology. So when you're on a racetrack, reliability is not as important as it is with a standard car or truck. We're not going to lose money. We're not going to get frustrated that we can't get to work if a race bike breaks down on a track. So we can find the real limits of the technology and take far more technology risks in doing that. And the other reason why we race is you can try out new ideas, different ways of building the bike, different ways of building batteries, and so on. So it's quite important when you're racing that you want to go faster, you want to beat other people. And it's that competition that drives the technology. The main race that we did with the bike was at the Isle of Man TT. The Isle of Man is a small island off the coast of England, and for 2 weeks every year they close the main roads around the island and you race bikes around the island. That track is 60 kilometers long, takes just over 20 minutes for the bikes to get round it, and it is one of the fastest, most dangerous road races in the world. It's a very exciting place to test bikes. And we, as a university, we've been racing big teams like Honda and so on. And we've managed to come second and third. Averaging speeds, 120 miles per hour is an average speed. So that's about 190 kilometers an hour average, including going around the corners. So quite high speeds and quite a good way to test the technology. That bike runs on batteries, and batteries are one of the limiting technologies for electric vehicles. At the moment, you will be familiar with your telephone, that your mobile phone has a battery in there. And most nights you will probably charge that battery. When we get to the point when you have to charge your phone battery once a week, then the batteries in electric vehicles, in cars, will not be a problem. But we need something to change. Now, this chart looks at the different chemistries that we've used in batteries over the last 50 years. And we started off with lead acid batteries. We still use those in cars today as the auxiliary battery. We had things like nickel cadmium, NiCad batteries, nickel metal hydride. And then today, most of the batteries we are using are lithium ion or lithium-based battery technologies. What we need in the battery industry is that next chemistry, something that is going to give us an energy density and a power density that's better than the lithium-based batteries we have today. Lithium-based batteries are getting better, but incrementally. We need another step change. And it's that step change which will mean that your mobile phone will be recharged once a week, and will mean that electric vehicles will have far more range than we need. So we need that next step. I don't know what that next chemistry would be. If I did, I would be very rich, have a large factory making them, and probably wouldn't be here to talk to you today. So all these electric motor drives that we've been talking about need a source of energy. On the motorbike, that's our battery pack. We need a power electronic converter, the motor drive, to control the electrical machine, and we have an electric motor. On the motorbike, we have no gearbox. We just drive a chain, which gives us a single speed reduction, and that drives the rear wheel. The system overview is very simple. As a rider, you get a display that tells you some of the things that's happening with the motorbike, particularly the speed, but maybe also the temperature of the motor and how much energy you have left in the battery pack. And you have one input to that system. And that's what you might think of as the throttle or the accelerator on a car, which is just a torque control. It's a pedal that you press on a car. What's a twist on the handlebar of a motorbike, which tells the controller how much torque the motor needs to produce. That torque control relates to the current in the motor, so we need to measure the current in the motor. And also the motor drive needs to know where the motor is, which is why we have a resolver on there. So quite a simple system. And we can spend a lot of time looking in depth at each part of that. What I've been asked to talk about today is the power electronics that you could use in these types of application, and where that technology is going, how that's changing, and where we're going to see technology development there. So the big challenges in power electronics, in that control of electrical machines or the control of electrical energy in power systems, is all about making things reliable. It's all about making things very integrated. It's all about the through life cost, so relating back to reliability, how things fail, how things break, smaller, lighter. And there's a big issue in this industry at the moment, because it's quite new, because it's expanding rapidly. There is a lack of skilled people. So professors such as Marco Riviera and myself are under a lot of pressure to make sure that in the future we have more and more students studying these topics, because the industry needs more and more people in this area. So, what does a power electronic system consist of? Well, the whole point of a power electronic converter is to take electrical energy in one form and convert it to another form. So in the motorbike, we're taking electrical energy from a battery, and we're using that electrical energy to power an electrical motor. So the battery is our supply and the electrical machine is our load. The power converter itself consists of power semiconductor switches, maybe some inductors and capacitors, to actually make that transformation in the characteristics of the electrical power. We need something to control all of this. So there's usually a microprocessor or some other form of digital electronics or even analog electronics to provide that control. That needs to know what's happening at the load, for example, the speed of the motor, the current going into the electrical motor. It needs to know about the supply, what voltage am I being presented with. And it needs some feedback from the power converter, particularly around health, temperature, what might be happening in there. And the controller needs to provide control signals to control that power electronic converter. So any power supply that you see, even the charger for your mobile phone, has exactly those same characteristics. Some power converter, some control, and some measurements. One of the things that we often see when we're looking at transportation platforms, particularly aircraft, is whether we should have a DC bus or an AC bus. And this is something that's been argued for decades. And if you look in your car today, then the 12-volt electrical system for the auxiliaries is a DC system. If you look in your house, then it's an AC system. Because the reason we use AC systems for the power utility is because we want to be able to change the voltage, so that we increase the voltage for long distance transmission and decrease the voltage when we come into houses or factories. The reason we might use a DC system is because it's simpler, it's easier to use, and it's often cheaper. We have fewer conductors and so on. If we were to redesign the utility system today, we would probably use DC, because we have power electronic converters that enable us to change the voltage of a DC system. But when they first started creating electrical networks and creating the electrical utility system, they didn't have that ability, so they used transformers. And transformers do not work with DC, they only work with AC. And that's why we have an AC system today supplying our homes and our industry. But that's why on transportation systems, you may commonly see a DC system. DC system also has the advantage that the batteries store DC. Now, if we have a DC system and we want to convert to an AC load, for example, to control an electrical motor, then we need to use a power electronic converter. And as you've either learned or you will learn, there's various different topologies, various different ways of doing this. The example on the left there is a 2-level inverter. It has 6 switches to control a 3-phase AC load from a DC source. And it does this by switching each output to be either high or low. And you can see it doing that in the graph at the bottom there. And you can see the average of that switching waveform is effectively a sine wave. If we split up that DC voltage into multiple levels, we can get multiple steps in the waveform. And that's what you can see on the right-hand side. What we can see on the right-hand side there is a 5-level waveform where there's a number of levels and the output is switching between those levels. The advantage of that multiple DC steps in that waveform is that we've already got a better approximation to the sine wave. So the multi-level converters have advantages in being able to give us better quality waveforms. If I'm controlling a motor, that means I will have lower losses in that motor or in the power electronic converter. The disadvantage is it's more complicated, has more devices, and therefore potentially more cost. It's more expensive. And that's the problem that we will see with those. This slide is looking at some design choices. In this case, it's for the electric motorbike. And we can see that there's various different topologies, the 2-level and 3-level converter that I've just been talking about, or even having more than one power converter driving one motor. So lots of different designs of topology. But the switching devices themselves is where the action really is. It's where the new technology really is in power electronics today. For a long time, we've been using silicon-based devices, particularly silicon IGBTs and silicon MOSFETs. In the last 10 years, silicon carbide devices have become available. Now, silicon carbide devices have lower losses and can switch more quickly. So all the limits that we had 10 years ago in our design of power electronic converters have changed. And this has changed the whole way in which we have to think, design, and build power electronic converters. This chart just tries to show some of those advantages. So if we look in the bottom pictures, the black line is showing the best we can do with a silicon device in terms of the efficiency of a power electronic converter. And the blue line shows what we can do with silicon carbide. So this is exactly the same power electronic converter, designed in the same way and using 2 different switching frequencies. The one on the left is 20 kilohertz, the one on the right is 40 kilohertz. You might ask why the black line on the right-hand side doesn't go up to the full output power. And that's because it can't. The losses are too high and the converter will not survive. It will get too hot. So we can see that the silicon carbide makes that power electronic converter far more efficient. It's a little bit more expensive, and that's where its disadvantage is at the moment. You have to pay more money, but you save a lot of energy and you can make the power converter smaller and lighter because it's switching faster. And so we have more efficiency and smaller and lighter power electronic converters. And that was the key technology to make our motorbike go faster. We can make a smaller, lighter power converter that not only was smaller and lighter in itself, but because it had a higher switching frequency, it made the electrical motor more efficient as well. And therefore, we had more energy to make the motorbike go faster. And the motorbike was also lighter because the power electronic converter was lighter. Now, when we look at power semiconductors that we need in power electronics, I've just been talking about silicon, Si, being the older technology, and silicon carbide being the newer, better technology. And you might think that that's the end of the story. But there are devices, particularly gallium nitride, are now available, which also have some characteristics which makes them just a little bit better. But the ultimate power semiconductor would probably be diamond. If we can work out how to use nanotechnology to make carbon into diamond semiconductor devices, you can see in that chart how all those numbers are significantly higher for diamond than they are for any of the other materials. So we're not there yet. There are other device materials out there which we can use to make power semiconductors. And when we do that, those power semiconductors will make power supplies, power electronic converters more efficient, smaller, lighter, and enable us to think of solutions as engineers that we can't think of today. So a lot of work to do there. There's other things we can do as well in the meantime. Diamond devices are probably still 20 years away. So we've got a long time to wait for that. In the meantime, we can look at packaging. We can look at how to make things smaller by packaging them in smaller spaces. And the mobile telephone industry has been very good at doing this with communications. We need to learn to do this with power electronic converters to make things smaller and to package everything together into smaller boxes. And when we do that, we find two things. We find we have to be very careful over the thermal design, but we find electrically the power electronic converter will work better and it will have this advantage of being smaller and lighter. So challenges, particularly are in the cooling, but a lot of advantages in terms of the application. Finally, it's very easy to think that this is all about the power semiconductor devices. It's not. We have other components, passive components like capacitors and inductors. And it's very easy to think a capacitor is a capacitor, but there's lots of different materials, lots of different ways of manufacturing those. And they all have advantages and disadvantages. So the electrolytic capacitors give us the highest energy density, but they have a poor lifetime and sometimes quite high losses. Other things like film capacitors, so the metallized polymer film capacitors, have a reasonably high power density, but a longer lifetime, but a limited range of temperatures of operation and so on. So we always have to choose the type of capacitor we need in our application based on the requirements of that application. Do we need long life? Do we need something that's very high in power density? And the problem, even with capacitors, is you can't get all those optimum solutions in one capacitor. You have to make a compromise. Everything in engineering is always about compromise and optimization, and capacitors is exactly the same. Talking of optimization, one thing we found in the design of electrical machines and in power electronics is that people are not very good at optimization. Computers are better at optimization. So in the design of electric motor drives, so the electrical machine and the power electronics, one of the things that we've seen and we do is optimization of design using a computer. Now, this is just a simple example looking at the aspect ratio of an electrical machine, so the length and the diameter of an electrical machine, and just optimizing around those 6 parameters that are listed there, which affect the diameter and the length of the motor. And with this example, we built some models that were scalable, and then we used a particle swarm optimization. The optimization algorithm itself does not matter. It takes months or sometimes even years to write all the models. and it takes maybe 1 or 2 days to do the optimization. You might find a different optimization algorithm is quicker, but if you spent months writing the models, it doesn't really matter if it takes a weekend to do the optimization. And you can see there that our engineer's best guess was that the electrical system weight, so the power electronics and the electrical motor, was going to weigh about 5.5 kilograms in this application. After the optimization of just those 6 parameters, that went down to 3.2 kilograms. So 5.5 kilograms down to 3.2, just by using a computer to do that optimization rather than a design engineer. Just to finish on at Nottingham, I've talked about the motorbike we've done. We've also got an aircraft, so that is a single-seater aircraft, and that is now fitted with an electrical motor, a power electronic converter, and a battery pack. And hopefully next week, we will actually be trying that out on an airfield. So it's taking the same technology that we've used in the electric motorbike and in electric cars, and putting that on an aeroplane. So we're looking forward to that demonstration. So in conclusion, the electrification of transportation is happening. Power electronics and electrical motors are key technologies, as is the energy storage system, batteries, and so on. With power electronic converters, there is not one solution. There's lots of topologies out there and lots of things that are happening, particularly around power semiconductor devices. The silicon carbide devices that we're now seeing have a lot of advantages in terms of the losses and the temperature, and we need to do a lot of work to take the full advantage of those devices. I expect it will be another 5 to 10 years before we've really got the optimum solutions in the packaging and the weight and volume of power converters as a result of those new technologies coming along. So thank you very much for listening. I hope you found that interesting. If you have any questions now, I'm very happy to answer questions. And if you have any questions later, please do send me an email and I will do my best to answer those. And finally, thank you very much for listening. And thank you very much to your professor for inviting me along today. It's always great to talk to people. And as I say, I hope you found some of that interesting. So thank you very much for that.
Thank you very much, Pat, for your presentation. It was very interesting, very complete as well. And now we will have some time for questions. I will switch between English and Spanish. Si alguien quiere hacer alguna pregunta, la puede hacer en español y yo la traduzco, o la puede escribir en el chat. Okay. Felipe Herrera, do you have a question?
Yes, I have a question. Hello, Professor Patrick. Thank you for your presentation. It was very interesting. Regarding the design of power electronic converters, how do you start designing a power electronic converter? What is the workflow that you follow?
Right. So the first thing you need really is the requirements. So what is your supply? What is your load? What frequency is the load going to be? And what power level? So therefore, what currents are you going to have? And you start with a pen and paper, usually, because you need to do some calculations. You need to think about what current is going through that converter, what voltages are going to be switched, and so on. So you need to do some very basic analysis to see what you're going to do there. And that will start to give you some ideas about the topology you need. So do you need that so let's just think of a motor drive application, like in an electric vehicle. Typically, you've got a DC supply and you've got an AC motor load. You need to start thinking about what devices you're going to use in there, and therefore which topologies you're going to use. Can you do it with a 2-level converter? You're going to have a 3-level converter, and so on. And that's when you need to use simulation. So typically we'll use a simulation tool such as Plex in MATLAB Simulink or something similar. So there's plenty of simulation tools there that allow you to design that power electronic converter and get some simulation results. One of the things about power electronics is that nobody believes you if you just do simulation, because there's a lot of things you then need to learn about how to build a power converter. So the next stage to that is what we think of as validation. Let's actually build a power converter, either full size, so you can test it in the application, or maybe a scaled model of part of it just to validate your simulation results. And so you then tend to do that build, control, design, and test phase of it. So that is quite a long period of time, depending on what you're designing, what you're building, and exactly what you want it to do. But there's a lot of things to think about through that. So that's a little bit of a summary. I hope that's okay.
Thank you. Yes.
Marco, I've noticed some questions in the chat. Do you want me to go through them?
Yes. Okay. I don't know if you want, I can read them, or you can read them and answer.
Go on. Do you want to read them out and I'll answer them one at a time? That will work quite well.
Ignacio Cárdenas asked how can manage the store for aircraft lithium ion in the sky.
This is
on the battery. Sorry.
Yeah, this is the battery. Yes, I understand.
Yeah.
Right. Okay. So there's a number of things here. One, whenever you store lots of energy in a small space, it can be very dangerous. Because if that energy escapes too quickly, you have fire. And that's what happened with the original lithium-ion batteries in the back of the Boeing 787. They caught fire. Not good. So one thing is you have to manage your battery very carefully. So having a good battery management system to make sure the battery is always safe is a good idea. The telephone industry, Samsung had that problem about 10 years ago as well. The other problem with batteries is on an aircraft is to make sure you have enough to, if you're going to use those batteries to power the propulsion of the aircraft, you need a lot of batteries. And long distance aircraft won't happen with batteries until there's a new technology. So we won't have lithium based batteries for long haul aircraft, but you might for short regional aircraft. And that's why the hybrid technologies are being considered in those sorts of applications. I don't know if one of those two answers your question.
Yeah, can I make another question, but in the same way? So you talk about the PMSM motor in the aircraft. Why? But it's lose when you are at high speed level, you lose Profe, no sé, me confundí acá. ¿Me puede ayudar un poquito?
Sí, dime lo que quieres decir.
A altas velocidades pierde, por así decirlo, el accionamiento no funciona bien. El accionamiento...
At high speed, the actioner doesn't work very well. This is what Ignacio was saying.
Okay, that depends on the design. When you're looking at these applications, you always design a motor for the application. Now, the examples I gave in this presentation tended to be permanent magnet motors, sometimes with surface mount and sometimes with internal mounted magnets. When you get to very, very high speed machines, you're better off with an asynchronous or induction machine, or maybe even switch reluctance, although they have some other problems, particularly around noise. So there's two things to this. You need to choose the electrical machine topology to meet the requirements of the application. So I agree with you. A standard permanent magnet motor is not always the best solution, particularly not at high speeds. But also you need to design the motor to meet the requirements of the application. And that does allow you then to look at how you use the power electronic converter and how you design the machine to meet the speed requirements that you have. So yeah, it's a complicated area, and permanent magnet machines are not always the answer. I totally agree with you with that. particularly not at very high speeds. The highest speeds machines we've built have been either switch reluctance or asynchronous motors, induction motors.
Super.
Good question.
Yeah. Benjamin asked you regarding another storage systems that can be potentially used into electromobility in addition to the conventional lithium battery.
Yeah, that's a good question. There has been a lot of interest in supercapacitors. They're very good for providing electrical energy quickly, but they have a lower energy storage density than a lithium-based battery. So a little bit of they can be useful in applications where you need lots of energy quickly. Other ways of creating the electrical energy, fuel cells are quite a good one. And you can get rechargeable fuel cells where the chemical reaction is reversible. And in some applications, we've looked at them particularly for things like submarines, a rechargeable fuel cell could be a good solution. So you can put the energy back into a chemical reaction and go both ways. So that can work. Fuel cells in a single direction, like a hydrogen fuel cell, is also another option there. Another one, which is one that they used on Formula One cars for a few years, is a flywheel. So actually a rotating mass. If you can get the bearings right and you can rotate the flywheel in a vacuum, then that can be a very efficient way of storing smallish amounts of electrical energy. But certainly there's been tram and bus systems that will use flywheel energy storage to get between stops and charging points. So yeah, I agree with you. Batteries is not the only solution. It depends on your duty cycles and depends on how far you need to go. So yeah, how much energy do you need to store? How long do you need to store it for? And so on. But there are plenty of different options depending on your application.
Super. In your slides, you show the typical configuration of civil aircraft and the configuration of the more electrical aircraft. And the Boeing has the Dreamliner 787, which is a very nice and quiet aircraft, but it has some problem with the batteries. So which is the configuration that they have right now? Is totally an electric aircraft or just some parts of the normal configuration?
So the Boeing 787 is a more electric aircraft. So what more electric aircraft means is the auxiliary systems are electric. So on the Boeing 787, all the air conditioning and pressurization of the cabin and the wing ice protection and some of the actuation is done electrically. But the propulsion is conventional. It's a big gas turbine.
Okay.
So the next stage to that is to make the propulsion electric as well. But you won't do that on a long-range aircraft like a Boeing 787 to start with. To start with, you'll do that on regional aircraft that only fly 300 or 400 kilometers. So we need to start that electric propulsion journey on smaller aircraft with shorter range.
And regarding the same idea, and based on the experience that the Boeing has, which are the main security issues regarding the storage part?
Well, the main thing, if you're going to use a battery like they do on, so the battery on the Boeing 787 replaces a small gas turbine. So in the tail of a conventional aircraft, you have a gas turbine and a generator to provide auxiliary electrical power. In the Boeing 787, they've replaced that with a lithium-ion battery. And what they didn't get right was they didn't get the battery management system correct. So the battery management system measures the voltages and currents in the battery and the temperature of the battery. And if the battery gets too hot, or if the cells of the battery get unbalanced, it will shut it down because it's in an unsafe condition. And that's probably what didn't happen quite correctly with the Boeing 787 batteries to start with. And they didn't get that battery management right. The other mistake they made was that they vented the battery into the passenger cabin so that when it caught fire, it put smoke into the passenger cabin. The other change they've made is to vent it to the outside, so that if a battery ever catches fire again, the smoke goes out of the aircraft and not into the passenger cabin. And that's important because passengers tend to panic when there's lots of smoke.
Yeah, I see. Nico asks, it's viable to create electric aircraft fed by solar energy, or it's the best idea to use batteries and charge cycles in land? For example, he remembered that NASA made a solar energy powered aircraft that had days of autonomy. What is your opinion about that?
It depends what you want your aircraft to do. Solar power is very good for aircraft that are going to spend a lot of time in the air, but don't need to move very quickly. So high altitude aircraft that are taking photographs of the land, spying on people, things like that. Those are all very good applications where the aircraft will spend a lot of time over an area, moving quite slowly. And in that case, solar is great. If you want to fly from the UK to Chile and you want to do that relatively quickly, then the wings of an aircraft are not big enough to supply the amount of energy you need to fly that aircraft. So you have to have another energy source. You might put some solar panels on the wings, particularly if they are very efficient, just to help. But at the moment, the weight you add to the aircraft, if you're flying at high speed, doesn't justify the installation of the solar panels. They're too heavy to actually help you in that high speed flight. So where it might be useful is if we're happy to slow down. We don't want, if we stop insisting on flying to places very quickly, then and maybe take 2 days to get to Chile rather than 12 hours, then maybe we'd be able to use solar power then. But at the moment, with the use cases, it doesn't work.
Thank you. Kata, as you, the idea of use cleaner forms of energy is to take care of the environment. But what happened with waste of batteries used in electrical vehicles, and how polluting are after their useful life?
This is a very good question, and there's two things we can do. If we use batteries in electric vehicles or electric aircraft, then one of the things that we might do is a second life, maybe to use those batteries in ground-based applications to support the electrical grid. When we put lots of wind and solar power into our electrical networks, we have a problem because the wind doesn't always blow, and in the UK, the sun doesn't always shine. So if we have lots of second life batteries, we can use those as a store of energy for when we have high usage of electrical energy in the utility. The other thing we can do is to design batteries so that we can recycle them. And there's a big push in that industry, a lot of work in that industry to design batteries in such a way as when they have life expired, we can take them apart and reuse the materials in them. So actually designing to be recyclable is quite an important part of that as well. And to answer the next question that's come up, which is a very good one, it depends. It depends on the usage of the vehicle and the temperature which the batteries are kept at, but typically somewhere between 5 and 8 years, maybe up to 10 years if you look after them. So in a vehicle, the lifetime of that battery, somewhere between, let's say between 5 and 10 years. That is assuming that you want the range of your vehicle to stay within 80% of what it is when it's new. You'll be familiar with your mobile phone, that when your mobile phone is 2 or 3 years old, the lifetime of the battery is less than when it was new. Exactly the same with your vehicle. If you were happy to take it down to 50%, then you might be looking at 15 to 20 years. So it depends on what you're happy for the range to degrade to.
Thank you. Regarding the control system, can you talk about the control that are used, especially in electric motorbikes?
So the control on the electric motorbike is about the same as any electric vehicle. There's a display to tell the driver what's going on, and there's an accelerator, a throttle, and that's the input to the control platform. And the control platform is typically a microprocessor which does the calculations and makes the decisions on how to control the power electronic converter based on measurements, in the case of a motor drive, of the currents and the going into the motor and the position of that motor. So we use a standard little microprocessor that we buy from Texas Instruments usually to do that job. Standard little control platform, typically these days programmed in C. And those microprocessors come with the peripherals, the connections that you need to control a motor drive. They're already built into the chip for you. So they're quite simple to implement when you get the right one.
Great, thank you very much, Pat. I have just a final question for you. More than a question is asking your opinion. I know that you are very involved with Chile, and you have been visiting Chile for the last 20 or 25 years, I don't remember well. And the students that are attending this seminar today, they are just starting in the electrical engineering career. So what is your opinion about the Chilean electrical or electronics engineer regarding and how they can affront all these challenges you have mentioned in your slides?
Well, yes, yeah, it is. I've been visiting Chile for more than 20 years, and when I first visited Chile, the amount of electrical engineering in Chile and the number of universities teaching good modern electrical engineering was very low. And it's very good to see both the industry in Chile, the government in Chile, and the universities in Chile all teaching more students, having more involvement, and that industry growing. It's got a lot of potential to grow. Chile is a very rich country in terms of natural energy sources. And there's lots of challenges. You're a very long country, one of the longest in the world. So transporting electrical energy is quite a challenge. So there's lots of challenges in Chile, lots of opportunities in Chile, lots of solar energy in the north, and quite a lot of wind energy in the south. So lots of things for electrical engineers to do. And as I said in my talk, there is a skills shortage in this area. So we've got lots of exciting technologies. And the other thing I would say about the Chilean universities is they do some of the most exciting and innovative research in power electronics in the world. If you look at the papers that win the best prizes at conferences and so on, Chile is very, very well represented, far higher grade than you would expect from the population. So the quality of your professors in Chile is very, very good. That's why we like working with our colleagues in Chile and have done for many years. So I'm not sure if that's the answer you wanted, Marco. But
it's.
But you've won too many best paper awards at conferences and in journals.
Yeah, and it's important to mention as well that University of Talca is the university with more publication that the University of Nottingham and the Faculty of Engineering has.
Oh yes, the Universidad de Talca publishes more joint papers with the University of Nottingham than any other university on the planet. Yes.
So I don't know.
We have very, very strong and very, very productive links there. It's very, very good.
Leo, ¿quieres preguntar algo?
Sí, Professor Patrick, in the last part of your presentation, you talk a little bit about optimization algorithm, and my question is, do you use neural network to improve the optimization algorithm? And if it is yes, how useful is the knowledge about neural network?
We have used neural networks. The example I gave you, so we have used neural network-based optimization. We've used it in control as well. But the easier optimization techniques to use in design are things like particle swarm. We've used artificial intelligence techniques as well. But as I was saying, it's using the ones that are convenient in the MATLAB toolbox is usually the priority there, because writing the models is the thing that takes the time. Neural networks do have their uses, and it is I give a whole nother talk about neural networks, but it is one of the techniques you can use. It does work, and it will work in real time for control problems as well. But it's not the one. It's not the one my PhD students tend to use, and I think that's because it takes them longer to set it up than it does with particle swarm, despite the fact it might actually be a faster solution.
And how difficult is use the MATLAB toolbox toolbox of neural network? Do you know about that?
I have to admit that I have various PhD students use that, and I do have a colleague who specializes in that area. It's not I've never used it myself, so I'm afraid I won't comment on that one. But if you contact me by email, I'll put you in touch with somebody who does know.
Thank you very much.
Thank you, Pat. The last
Marco,
question from Nicolas.
Yeah, I'm afraid at that point I've got to go. I need to be somewhere else. But I will just pick up that one last question. Yeah.
Yes, please. Do you want to read them?
Yeah. So the question is around. It's not ceramic semiconductors. It's around ceramic capacitors, and they become quite fragile. And you can do things with packaging to reduce that problem, but then you've lost some of the advantage in terms of the density, because they'll end up being bigger. So yes, you can do things with packaging to protect them, you can enclose them and so on, but then you lose some of the advantage that you tried to gain by going down the route of the ceramic semiconductors. But they are very useful in applications where you have higher temperatures, and that's why you might use them.
Thank you, Pat, for your time and your presentation. Now you are free to leave us. We will continue working because we have a few more hours of course. Thank you very much.
Thank you. No, thank you very much. It's been really nice, and thank you all very much for your questions. It's been good fun. Thank you.